A standard light bulb is a bit of a mess. It throws energy in every direction, filling a room with scattered light. But a laser pointer takes that same energy and organizes it into a single, hyper-focused beam. Lasers do this by focusing photons, the tiny, individual packets of energy that make up light, so they all move in perfect synchronization. Imagine if we took that same level of organization and applied it to sound and physical vibration. At a microscopic level, sound is just the physical jittering of atoms. Scientists call the individual units of this jittering phonons. A phonon laser, or Sacer, takes those chaotic, jittering atoms and funnels them into a synchronized line. Instead of a beam of light, you get a perfectly organized beam of sound. By turning random mechanical noise into a controlled signal, we gain a new level of precision over the physical world. There is one major difference between light and sound. Light can travel through the emptiness of a vacuum, but sound requires a medium, like a solid, like a liquid, or a gas. It needs atoms to physically bump into one another to move. To create a sound laser, researchers use optical tweezers, focused beams of light, to hold a microscopic silica bead suspended in midair. By pumping energy into that trapped bead, scientists force it to vibrate with extreme precision, creating a steady, uniform beam of sound waves. Because these vibrations are so stable, these trapped particles can act as ultra-accurate mechanical clocks, allowing us to use the physical environment as a high-precision tool. This technology represents a leap similar to the move from bulky vacuum tubes to the transistor. It changes how we process physical signals. In high-tech environments, noise is the enemy. Even the tiny vibrations from a truck driving past a building can interfere with sensitive equipment. This has led to the creation of phononic integrated circuits. These are chips that use pulses of sound instead of electricity. They use tiny pathways that act like traffic signals, directing sound waves to perform specific tasks. Phonon lasers solve the noise problem because they allow us to treat vibration as an organized signal. The systems can ignore the random noise from the outside world, and because they use sound rather than electricity, they don't cause any electromagnetic interference. By mastering these vibrations, we have turned what used to be a source of interference into a highly reliable sensor. This level of accuracy is possible because phonons have a much shorter wavelength than light at the same frequency. You can see the advantage here. While a light wave might be too wide to notice a microscopic object, a tightly compressed sound wave is small enough to strike it directly. This allows phonon lasers to detect tiny shifts in gravity or find microscopic cracks inside specialized materials. We are also seeing this applied to medicine. It works like an ultrasound, but with the pinpoint focus of a laser. This could allow for the imaging of individual cells. Because these sensors are microscopic themselves, they can perform these scans without the physical bulk associated with traditional large-scale imaging equipment. Wielding sound at this scale helps us bridge the gap between general diagnostics and the study of individual human cells. There is also a major role for this in computing. Modern quantum computers often struggle to transfer information between different types of systems. The phonon laser acts as a bridge. It can take quantum information and carry it from one system to another using sound waves. This allows completely different hardware to talk to each other, like moving data from a metallic superconducting circuit across the bridge and into a glass fiber optic cable. These lasers operate at frequencies far beyond what the human ear can hear. They do their work in total silence, but if we could perceive them, a phonon laser would be the most constant, pure note ever generated. It is a silent, physical symphony that provides the foundation for our next generation of sensors and computers.